The conventional gamma ray tool consists of a Geiger-Müller counter or a more sensitive sodium iodide scintillation detector and crystal, which counts natural gamma ray emissions for fixed intervals of time. These emissions originate through the natural decay of radioactive elements in the formation surrounding the borehole. The radioactive elements are due primarily to uranium, thorium, and potassium. As each of these radioactive elements disintegrates toward its end products, it gives off a spectrum of gamma rays of specific wavelengths. As shown here, uranium and thorium have characteristic spectra of wavelengths, and potassium has a single emission wavelength. The total count rate per time interval is plotted in API units, which have been established by the industry. The greater the count rate, the greater the API reading.
This calibration pit has been constructed at the University of Houston. In this pit, cement containing small amounts of disseminated uranium, thorium, and potassium salts has been sandwiched between two layers of untreated Portland cement. The API standard defines the difference in gamma ray activity between the untreated zone and the treated radioactive cement zone as being 200 API units.
A tool is calibrated by placing it in the pit and then equating the difference in readings to 200 API units. Since all tools cannot be run routinely through the test pit, field calibration sources produce known gamma ray emission rates. These are used to confirm that a tool is properly calibrated. Two common uses of simple gamma ray devices are correlation of stratigraphic units and estimation of shale content. Remember the gamma ray spectra for uranium, thorium, and potassium that we showed earlier. Sophisticated gamma ray devices add another general use to gamma ray logging. They measure the energy level of the natural gamma ray spectrum coming from the formation, and can determine what percentage of the total energy spectrum can be attributed to either uranium, thorium, or potassium. Results of gamma ray spectroscopy are presented in this format. In the left column are a total gamma ray curve and a uranium-free curve. On the right are curves of uranium concentration, thorium concentration, and potassium concentration. A change in mud weight, hole size, casing in the hole, cement thickness, or the position of the device in the hole, centered, eccentered, or tilted, will affect gamma ray count. Correction charts are available to compensate for the effect of downhole variables.